Good morning, everyone. I hope that you're all having a great week and that you're feeling okay today. We're looking at lesson 30.21 today, which is dealing with isotopes. And for the remainder of the course, what we're going to be looking at is what I can call nuclear physics. We're done with looking at atoms in terms of electron behavior. And every model of the atom that we studied so far has all been about the behavior of electrons. Well, except for the Dalton model of the atom, because Dalton didn't know about electrons. So what we're going to be doing now is delving into the nuclei of atoms. Nuclei is a word that's plural for nucleus. And in order to understand nuclei, we have to talk about what are called isotopes and isotope notation. This lesson can be found on page 21 of your current lesson handout. Now, you are also going to need to refer to, throughout this lesson, the periodic table. And in this course, every student is given a periodic table for exams. Of course, you're not writing exams, but you still have access to a periodic table. The periodic table can be found in our classroom shared folder, so you will want to have access to it. To begin with, here are some definitions. The atomic number of an atom is given the symbol Z, and what the atomic number tells you is how many protons are in the nucleus of the atom. And it's that number that identifies the type of the atom. For example, the atomic number of carbon is 6. So any nucleus with 6 protons in it is a carbon nucleus. When you look at the periodic table and you find carbon, it is in the 6th location on the periodic table. Hydrogen is atomic number 1. Every hydrogen atom in the universe has 1 proton. Helium is atomic number 2, and so on. So since helium is atomic number 2, every helium nucleus always has 2 protons. Isotopes of atoms are atoms that have the same number of protons, so they're the same type of atom, but they contain within the nucleus a different number of neutrons. So as an illustration, I'm going to be using these spheres to represent protons and neutrons. And if I have a nucleus that contains a proton and a neutron, and I have a second nucleus that contains a proton and 2 neutrons, then the atomic number of each of these nuclei, or each of these atoms that the nuclei are inside of, the atomic number of each is 1, which means they're both hydrogen, because they each have 1 proton. And the atomic number tells you where on the periodic table the atom or element or nucleus belongs. These are 2 different isotopes of hydrogen. The atomic mass number, which is given the symbol A of a nucleus, is the total number of nucleons in the nucleus. What the word nucleon is a word that describes protons or neutrons. So the atomic mass number of the nucleus on the left is 2 because there are 2 nucleons, 2 particles in the nucleus, whereas the atomic mass number of the nucleus on the right is 3. We use what's called isotope notation. And by the way, everything that we're learning today is so that we can be successful in applying physics to the remainder of the course. Isotope notation shows 3 pieces of information. It shows the atomic mass number of the nucleus, it shows the atomic number of the nucleus, and it also shows the elemental symbol. So to begin with, we have this chart that we have to fill out. Nucleus A has 92 protons and 143 neutrons. Since there are 92 protons, the atomic number is 92. Nucleus B also will have an atomic number of 92 because nucleus B has 92 protons. Now, what is the atomic mass number? If there are 92 protons and 143 neutrons, then we are going to have to add those 2 numbers together to get the atomic mass number, because atomic mass number is the total of all of the particles in the nucleus. So when we add those 2 together, we get 235 for an atomic mass number of nucleus A, and we get 238 for an atomic mass number of nucleus B. Now, what is the name of the element? If you go to your periodic table and you locate atomic number 92, and it might take you a while to find it, you will discover that it's uranium. And now we run into a bit of a problem because nucleus A is a nucleus of uranium and nucleus B is also a nucleus of uranium. So these are both called uranium. When we name them, though, we have to name the isotope with that information. So we can't just say uranium. We have to say that nucleus A is a nucleus of uranium-235. And we say 235 and not 92 because we already know it's 92. 92 is contained within the word uranium. Nucleus B is uranium-238. So what does the isotope notation look like? It looks like that. It's got two numbers on the left. 235 is on the top, which is the mass number. And then the atomic number is on the bottom. And then we have the elemental symbol. For the uranium-238, that's what the isotope notation looks like. All right, we're going to be doing an example now. In a nucleus of an atom, a typical distance between nucleons, which are protons and neutrons, is around half of a femtometer. Now, if we consider two protons that are that close together, they are pushing away from each other. And yet we know that in nuclei, when protons are next to each other, they stick together because the nucleus is stable. They must be attracted to each other somehow. Now we know that they're both positive, and that means they repel from each other, so there must be some other attractive force pulling them together, otherwise they would fly apart. And the first thing that physicists questioned is maybe the force holding them together is a gravitational force. It could be, because gravity is an attractive force. So as an exercise, we're going to be showing here that gravity cannot be responsible for holding these particles together in a nucleus. We're going to do that by calculating the attractive gravitational force between those two protons, and we're going to calculate the repulsive electric force that exists between the two protons. The top formula we learned about in Physics 20, and the bottom formula we've learned about in Physics 30. When we substitute all of the numbers into Newton's universal law of gravitation, we have 6.67 multiplied by 10 to the negative 11 Newton meters squared per kilogram squared. So when you look up the mass of a proton on your data table or data sheet, it's 1.67 times 10 to the negative 27 kilograms. I'm squaring that because we have to multiply by the mass of the proton and the mass of the other proton. We're talking about two protons. Divided by 0.5 femtometers. If you were to go to your data table and look up on the metric prefixes table, you would see that femto means 10 to the negative 15. So we have to divide by that squared. When we do the same thing with the electrostatic force, we're going to have Coulomb's constant, 8.99, multiplied by 10 to the 9 Newton meter squared per Coulomb squared, multiplied by the charge of the proton, multiplied by the charge of the proton, which will be the charge of the proton squared, divided by the distance squared. And what we get for the force of gravity is a very small force, approximately 7 times 10 to the negative 34. So gravity is pulling these two protons towards each other with that amount of force. The electric force, when we calculate it, is a whopping 902 newtons. Now, we've seen some big numbers in this course, but in terms of a force acting on these two tiny, tiny particles, that takes the cake. That is huge. To give you an idea of how big that force is, that would be the force required for you to lift an object off of the floor if the mass of the object was 100 kilograms, which is about 220 pounds. So the force is enormous. And don't forget that this is a repulsive force. And what we have just shown is, since the repulsive force is so much bigger than the attractive force, there is no way that gravity can be responsible for holding these together. If those are the only two forces acting between the protons, then the net force on each proton should be a repulsive one, and the protons within a nucleus should fly away from each other very rapidly. But obviously they don't, because atoms are stable. And we're doing this exercise so that we can review something that you touched on probably in Physics 20, but maybe you didn't, and that's that there are 4 fundamental forces in the universe. And over the next 2 weeks, we're going to be using the 4 fundamental forces. We're going to be using isotope notation to try to come up with a better description of what's going on in terms of matter and forces. So this is just setting the stage for something that we're going to use later. There are 4 fundamental forces: gravitational, 2 nuclear forces. One is called the weak nuclear force and one is called the strong nuclear force. And then there is a force called the electromagnetic force. These forces are listed from top to bottom in this table, from weakest to strongest. So gravity is the weakest of the 4 fundamental forces when we're talking about within the nucleus. Obviously, gravity is an attractive force between any 2 masses. And electromagnetic, we don't study this in detail in this course. We have studied electric forces and we have studied magnetic forces. It turns out that they are the same type of force. All electric forces and all magnetic forces can be described using an electromagnetic force model. There are 2 nuclear forces. The weak nuclear force is something that's responsible for particular types of radioactive decay that we will learn about in, I believe, 2 lessons. And the strong nuclear force is the one that is keeping those protons from flying apart. So the force that is overcoming that 920 newtons of repulsion is called the strong nuclear force, and it's an attractive force. If we were still in the classroom, I would be telling you that all of the other information is stuff that you could be tested on, but we are not, so you're not going to be tested on this other stuff. But if you have a handle on the different ranges and the relative strengths, then you will understand the physics that we learn a little bit later better. It turns out that the range of electromagnetic and gravitational forces is infinite. What does that mean? It means that no matter how far apart 2 masses are, there will always be some attraction between them. No matter how far apart a magnet is from a magnetic material, there will still be some magnetic influence. These forces extend to infinite distances. The strong nuclear force, and this will be important for later, only exists when the particles are less than a femtometer apart. So when you have 2 protons that are bigger than a femtometer away from each other, they are not attracted with the strong nuclear force. But if you can push those 2 protons towards each other, and it requires a lot of effort, and if you can get them really, really close, less than a femtometer apart, all of a sudden they will pull together. The strong nuclear force only exists over very, very tiny distances. The weak nuclear force exists over even smaller distances. The relative strengths are there just to give you an idea of the numbers that we're talking about. If we assign a gravitational force in the nucleus a value of 1, it turns out that the strong nuclear force is 10 to the 38 times greater. So the only thing I want to impress on you is that the strong nuclear force is huge compared to the gravitational force. When you compare the weak nuclear force to the gravitational force, the weak nuclear force is still huge. It's 10 to the 32 times greater. And it turns out electromagnetic forces are about 10 to the 36 times greater. Don't worry about the numbers in the column to the left of that. I meant to take them out in this version of the course. The bottom line is gravity is a weakling. All of the other forces in nature stomp gravitational forces. Gravitational forces are very, very weak compared to the other fundamental forces. And that's it for today. You have some questions dealing with isotope notation that will be on the next page of the handout, 1 to 8. We studied the 4 fundamental forces here because a little bit later we're going to have to refer to them to explain certain things that go on in radioactive decay and in nuclear fission and in nuclear fusion. And I would rather have that information in our arsenal right now than have to teach it to you when we learn about radioactive decay and fission and fusion. So a few questions to work on dealing with isotope notation. I hope that lesson made sense. Have a wonderful rest of the day, and we will talk to you guys soon.